Welcome back to chemistry. Today we're going to talk about the Birch reduction in general, then do a review of what it means to be a donating or a withdrawing group on the benzene ring, and then see how those donors or withdrawers affect our Birch reduction product. Let's get started. This is the Birch reduction reagent. Two equivalents of sodium metal and ammonia with an alcohol also present. In this case, I chose methanol. Let's see what happens when I treat benzene with this reagent. Well, benzene is an aromatic ring with 3 conjugated pi bonds. What do we end up with? This. Well, we have 2 pi bonds left across the ring from each other. They're not conjugated, therefore we don't have an aromatic system. Also, we added 2 protons onto the ring. Where did they come from? The OH group, right here on the alcohol. What really happened was that the sodium metal dropped an electron into the benzene ring, which picked up a proton, and the other equivalent of sodium metal dropped an electron across the ring, which also picked up a proton. Where the electrons were left was where the pi bonds were formed. We're going to see this in a lot more detail and the reasoning why in just a second. Let's do a little Organic 1 review. We all have been asked in Organic 1 to compare the stability of tertiary and secondary carbocations, and we reflexively say the tertiary is more stable. But why? Well, the tertiary has 3 alkyl pumps. That is, the 3 methyl groups attached to the positive carbon pump electron density down their sigma bonds, stabilize the positive charge. Tertiary has 3 pumps, secondary only has 2, so that's why the tertiary is more stable. What can we conclude? Alkyl groups are electron pumps, or donors. Another group you're going to see on the benzene ring that could be a donor is ether group. That oxygen with the lone pair is great at donating charge into the ring. Let's look at a withdrawing group here. Well, we've got an electronegative oxygen that unequally pulls on that bond and takes electron density away from the carbon, making it partially positive. That carbonyl carbon is quite reactive because of that positive charge, and we do a lot of reactions at that site. That positive carbon in turn pulls on what's next door, which is of course the benzene ring, making the carbonyl group an electron withdrawer. Another common withdrawer that you'll see is this one, the nitro group. That positive nitrogen is great at pulling electron density away from what it's next to, which again would be the benzene ring in this case. It's so good that we say in most contexts it will in fact be our best withdrawer on the benzene ring, both for this and in EAS. Let's do Birch reduction with groups. Well, I'm going to do something a little funky, so pay attention. We've got 3 pi bonds in benzene, each with 2 pi electrons, which means we have 6 pi electrons in benzene. We also have 6 carbons, so that's about 1 pi electron per carbon. So I'm going to draw 1 pi electron per carbon. Now let me add a group on. Here's an alkyl group on the benzene ring. That's an electron pump or donor, as we just discussed a minute ago. Well, it's going to pump density into the ring, making that carbon partially negative. There are several ways to solve this problem. The most accurate is using a LUMO map. A lot of professors don't give that, so I'm going to show you a less chemically correct, but still valid way of getting the correct product for product prediction purposes. I'll show you both methods right now. So let's take this molecule and treat it with our Birch reduction reagent. Sodium has to drop in its electron into the ring. Well, if we have the LUMO map as shown, we can see where the LUMO is, the lowest unoccupied molecular orbital. Well, sodium's going to drop into the LUMO. Notice, as denoted by the X's, where there are no spheres. Those are called nodes, and we say no electrons go to the node. So we're going to drop the electron where there's not a node, at the LUMO, right there. Okay, what if we don't know this? What if we don't have the map? How do we rationalize this? All right, well, we have a negative electron on sodium, and we've of course got that partially negative carbon at the top of the ring. Truth be told, all the carbons on the ring are partially negative, but the one at the top is going to be the most partially negative because it's closest to that electron donating group. So sodium's going to prefer to drop the electron where it's not quite as severely partially negative. Again, this isn't exactly quite good chemical reasoning, but it will lead to the correct product for product prediction purposes. Now we're left with a negative carbon, and of course, the negative carbon picks up a hydrogen from the alcohol, and we drop another electron off across the ring at what's called the SOMO, or the singly occupied molecular orbital. So, we attach our first proton, we drop an electron across the ring, and attach our second proton. Look at where the pi electrons remain. Well, connect the dots, and we end up with our final product. Note, of course, that the hydrogens came from the alcohol. That alcohol could have been deuterated, for instance, and then you'd have a deuterated product. So let's summarize. Find whether the carbon on the benzene ring bonded to the group is partially positive or negative. Assign one pi electron to each carbon. If you're given a LUMO map, go ahead and drop the electron at the LUMO, and then drop another one across the ring at the SOMO, and add protons at both of those sites. If you don't know that, do just what we talked about. If you have a delta plus, drop the electron right at the delta plus. If you have a delta minus at the carbon connected to the group, add the electron next door. Then, of course, the other one across the ring at the SOMO, and draw your double bonds where the pi electrons remain. That's a lot of words, so let's put it into practice with a different example. I'm going to work this one without doing a LUMO map, because in most cases you're not going to have one for a lot of professors. Alright, first let's determine whether the ring carbon bonded to the group is partially positive or negative. Well, that carbonyl carbon is partially positive, and we can even draw a resonance structure, giving it a full positive charge. That, of course, in turn, will pull electron density out of the ring, making the carbon of the ring partially positive. So, let's go ahead and assign a pi electron to each carbon. Then, let's add the proton to the delta plus site, and, of course, another one at the SOMO across the ring. Perfect. Now, all we have to do is connect the dots and draw the double bonds where the pi electrons remain. And that will lead us to our major organic product. What's important to notice here is that the double bonds end up in a different location relative to the group, depending on whether that group is an electron donor or a withdrawer. If you follow the steps as we outlined just a moment ago, you should be able to get the correct product every time without doing any kind of memorization about what the product should look like if the group is an electron withdrawer or an electron donor. That's it for chemistry for today. Thanks for your attention, and good luck.